Yeah, welcome to my course on Nonlinear Optics. Nonlinear Optics, strange name, isn't it? I will say a few words on what is meant by nonlinear optics in a few minutes. But first, I have to discuss a little bit of Corona stuff. As I told you in my email, I will teach this course as a so-called hybrid course. So there are students here, and there are students at home or wherever at their computers, and watch us live on YouTube. I'm very happy that you are here. It's much better than teaching here in an empty room, and I appreciate very much that you came. In order to produce a decent live stream, or a live stream of a decent quality, technical quality, we worked with our alumni Simon Stützer and René Hallmann. Here you see both these two guys. They are professionals in the field of live streams, and they designed, built, and installed this system for us. And what you see what they usually live stream: boulder, so climbing sports and other stuff of sports. So they make a living out of that, and helped us here with this technology. Today I will mostly use slides, but you'll see that we also have a very nice system. Actually, I can demonstrate it here. Yeah, so when I would write notes on the blackboard, I instead use here an iPad, and you can see that the quality is really nice. Yeah, so this is how it will look like. But as I said today, I will mostly show slides. So this is how it looked in the last semester. So we tried this already out in an undergraduate course last semester, and I hope that this is good, well readable. Okay, so there's one thing I would like to point out. What you should do at home is to make sure that you have high HD quality. Yeah, so there's this button on at the bottom of your YouTube window, and you should make sure that you have HD quality. It's the first use of this system today, so if something doesn't work well, then my apologies already at this point. But actually, I have support here by my colleague Felix Wiesner, who is trying to manage this today. And he will also answer the chat, the YouTube chat. So if you have questions, then Felix Wiesner would forward this to me. So these are the technical aspects of Corona. Now the real Corona stuff. It's my utmost priority here in this lecture that this setting is safe, so that you feel comfortable to come. And we did considerably more than required by the university administration in order to realize that. So the first thing is that we reduced here the number of seats from 15 to 12. We installed this shield here. I know it doesn't help the image quality, but if I would not have it, I would need to wear a mask, and this would not help the audio quality, which is always more important than the video quality. We'll air this room regularly after 20 minutes. Today we can keep the window open because the weather is so nice, so this doesn't apply for today. But if I would forget this in a subsequent lecture, please remind me that we open the windows every 20 minutes for 2 minutes or so. Last not least, we bought these devices here. So these are UVC devices. So there are UVC lamps inside in this enclosure, and there is a ventilator that sucks in air, and UVC is known to be very effective on viruses, bacteria, and so on. So there's a second actually here behind. So this is an additional measure that we have taken. And you have already seen at each seat we put a form where you can, or where you have to provide contact information. The university requires you, in addition, to use this system here with these QR codes. I hope everybody knows, is aware of that. Once I'm convinced that their system works well, then we may forego these forms. Okay, well, back to optics and to nonlinear optics. Optics is a venerable field of science, isn't it? It's the oldest branch of physics. And the father of optics is Ibn al-Haytham, whom you see here. He certainly looked differently. Yeah? So this is just a fantasy picture that in later centuries were made up. He was a mathematician. Yeah? In the Western world, actually, he's known as Alhazen. He was a Yeah, so this is Alhazen. Yeah? Alhazen, a mathematician, an astronomer, a physicist, and one of the towering scholars in the Islamic Golden Age about 1,000 years ago. What you see here is actually the reprint of his most important work, which is the Book of Optics. And this reprint is from 1570s or so, right? So more than 500 years after his death. So you see how important he was or has been considered. I think it's fair to say that he is for optics what Newton is for mechanics. Yeah? So he's the Isaac Newton of optics. And well, the fact that today, at least in the Western world, he is more or less unknown. I'm not quite sure where this comes from, but cultural things may play a role there. It took 900 years after Alhazen to unravel the nature of light, when Maxwell succeeded to unify the then most modern branch in physics. Yeah, so in Maxwell's times, the most modern branch in physics was electrodynamics or electricity. So Maxwell famously managed to unify electricity or electrodynamics and optics. And so he succeeded to unify it with the oldest discipline, namely optics. Yeah? And Heinrich Hertz famously proved Maxwell right by discovering radio waves. Yeah? So Maxwell introduced this Maxwell displacement current, as everybody knows in this room, I guess. I said that Maxwell succeeded to unravel the nature of light. Well, which is, of course, not quite true, because the nature of light is, of course, quantum. And if you want to read about this, yeah, so QED was one of the major contributors to QED was Richard Feynman. And if you want to have an introduction to this field, an easy introduction to the field, then in Christmas holidays, you may want to read this book, which is, of course, also available in English. It was, of course, originally written in English. So now, nonlinear optics, strange name, you might say, but actually it comes from the following. Yeah? So in electrodynamics, in the undergraduate course of electrodynamics, electrostatics, actually, one would discuss polarization. And, well, I draw this kind of pictures that you see here, yeah, where you have dipoles, electric dipoles, and if you apply a field, then they kind of align, and then you can define polarization. And what we do is that we write the polarization in this form here. The polarization as being proportional to the field that is responsible for aligning these dipoles, right? And what I emphasize at this point in the second semester is that this law here, the significance or the way you should honor this or appreciate this law is by far not comparable to the Maxwell's equations. The Maxwell equations are laws of nature, whereas this here is just a power series expansion of something, nothing more. Yeah, so it's a linear approximation to the reality, not more and not less. Yeah? And what we are going to do here basically is that we carry on this power series expansion to the next and next terms. Yeah? This is what makes optics, what makes linear optics. Usually we don't say linear optics. When you speak about optics, then you usually mean linear optics. So nonlinear optics is if we go to terms beyond that. An interesting point is that sometimes you can't really do this because a power series expansion not always converges. And then you're in the non-perturbative regime of nonlinear optics. So even this expansion here does not work at all times. So a little bit of history of nonlinear optics. It started with Maria Goeppert-Meyer, and she did her PhD thesis in Göttingen with Max Born, a famous figure, in 1930, and it was entitled Über Elementarakte mit zwei Quantensprüngen. So in German, on elementary processes with two quantum leaps. Göttingen was a very famous place at that time. Yeah, so this was just before the Nazis came to power, who expelled then all the scientists, the Jewish scientists and also others. So 3 Nobel laureates were, or 3 later Nobel laureates would attend her PhD defense. Yeah, so which PhD candidate has this honor? She later married Joseph Edward Meyer, who was an American chemist working with Frank, who was one of the Nobel laureates attending this defense. And this chemist, this American chemist, not only became her husband, but eventually also the president of the American Physical Society. So a chemist as the president of the American Physical Society. Maria Goeppert-Meyer was the second lady to receive the Nobel Prize. She didn't receive it for predicting nonlinear optics, but for her development of the nuclear shell model of nuclei. Yeah? Why did it take so long for nonlinear optics to become a reality? This has to do with the laser. And you see here 2 people, 2 men, Theodore Mayman, who invented the ruby laser in 1960, and here a little bit of local patriotism. Here you see Reinhard Neubert, who built the first gas laser in Germany in 1962, so just 2 years later. And you see him as an old man, I would say. I hope he doesn't listen. You see him as an old man receiving an honorary doctorate in the great lecture hall here in this building. And you also see his laser, the first German gas laser, helium neon laser. It was mounted on a heavy Zeiss machine bed, and there was a famous lecture well, still in 1962, where they did a series of remarkable experiments. So this picture is actually also a picture from the great lecture hall in this house. Yeah, it is known which kind of experiments they did. Yeah? So the laser, what you need, as I mentioned already, that we are talking about a power series expansion, and it is evident that, well, that the next order would need high field strengths in order to, yeah, to make a noticeable contribution. So once the laser was invented, the discovery of nonlinear effects began. And here you see a paper actually from 1961, so immediately after the discovery of the laser. And this is whom you see here is Wolfgang Kaiser, a German physicist who worked at that time at the Bell Telephone Labs, famous lab, no longer in existence in this form. And he later became a professor at the Technical University in Munich. And he is one of the pioneers of femtosecond lasers. He probably built the first femtosecond lasers in Germany. And he discovered the first nonlinear effect. Yeah, so it was the excitation, the two-photon excitation. Yeah, so kind of what was predicted by Maria Goeppert-Meyer. This here is Peter Franken, and he discovered, or he was the first to measure or the first to see second harmonic generation. We will talk about this figure from Physical Review letters in, well, later this course. But second harmonic generation arguably is the single most important effect in nonlinear optics. And at that time, it was high-end science, but today you find second harmonic generation in each green laser pointer. Yeah, so what you see here is a typical laser pointer. It consists mostly of the batteries. And then you see some electronics here with an infrared laser diode. Yeah, so it's shown here, the infrared laser diode. And then this infrared light from the laser diode is focused into a so-called nonlinear crystal. Yeah? It's called nonlinear crystal because it does nonlinear optics. Yeah, so otherwise, there's nothing nonlinear in this crystal, or nothing more or less than in other crystals. And then you have a few lenses in order to collimate the beam. And today, you can buy this for a few bucks. Nonlinear optics became a huge field meanwhile. So in these 60 years since the first observations of nonlinear effects, nonlinear optics made a huge career. And therefore, this 2 hours course can by no means cover nonlinear optics completely. And actually, if you look at the lectures that we offer within the Upper School of Photonics, then you will see a huge series of lectures where nonlinear optics plays a role, sometimes even a dominant role. And I show this here from the web page of the Upper School of Photonics. And I marked those in red where I believe at least that nonlinear optics plays a role, sometimes even a major role. Yeah, so this is here the second semester, and you find similarly many in the third semester. So therefore the question, what are we going to do here? Well, we will cover the classic curriculum of nonlinear optics. And the most important part that will be treated here are the coupled wave equations. Yeah? So we have to prepare a little bit by repeating some concepts of linear optics, and we'll see that within linear optics there are already some effects, in particular the Paulus effect, so the electro-optic effect, that gives already, well, a glimpse of nonlinear optics. Actually, a little bit more than a glimpse of nonlinear optics. So this is what we are going to do in the next perhaps 2.5 lectures. And then there will be an overview of nonlinear effects, very simple concept that we'll develop there. After that, we'll immediately, well, and this will already give some insights, some very valuable insights. We will not do much more than a little bit of trigonometry in this chapter. Yeah? But nevertheless, it will give quite some interesting insights. But in order to really understand what's happening with nonlinear processes, we need to derive the coupled wave equations. Yeah? And for this, we'll first look at nonlinear wave propagation and then derive the coupled wave equations. Yeah? So there are coupled wave equations for each and every process in nonlinear optics. Yeah? So for second harmonic generation, for some generation, difference frequency generation, and so on and so forth. A very important thing after that will be phase matching, which is already, well, included in the coupled wave equations, of course. And then we'll look at specific instances of nonlinear effects. So the most important one, some frequency generation, which is kind of the prototype of nonlinear effects. Then second harmonic generation, because it's so important. Well, we also look a little bit at difference frequency generation. And only after that, we will try to make the connection that we actually do for linear optics right away. Yeah? So we'll look at linear optics and the Lorentz model in the framework of a driven oscillator, of a driven linear oscillator for linear optics. And for nonlinear optics, we'll use an anharmonic oscillator. And also this will give some insights on the structure of nonlinear susceptibilities. Yeah? And, well, I probably have to leave out 11 and 12. Crystal symmetry I probably will discuss briefly because I think it's so nice and beautiful. But then we have to look at the so-called third order effects, in particular self-focusing and nonlinear pulse propagation. Yeah? So when you launch an intense laser pulse, say from a femtosecond laser, and you launch it just through air, say, then you can observe astonishing effects like self-focusing and things like that. Yeah, and as I said, this is by far not the end. Yeah, so I would like to cover a little bit or give at least a glimpse to these, but I'm pretty sure that time will not be sufficient because this semester is 2 weeks and this means 2 lectures shorter than usually, again, due to this corona crisis. Okay, perhaps a few more words on the organization of this course. The teaching assistants will be Dr. Matthias Kübel, and he will contact you soon and try to set up the recitations. We'll do it in the following way. There will be homeworks, of course. Yeah. And you're supposed to solve the homework problems. And we'll provide the solutions with a YouTube video. Yeah, so my colleagues will make a YouTube video so that you can see whether you did it right. We don't have the capacity, unfortunately. We don't have enough teaching assistants this time, again due to the corona crisis, in order to correct your homework. So what we offer in addition is an online discussion group. Actually, each week, 1 hour, not 2 hours, just 1 hour, so that you can ask about unclear things that remained open in the lecture. Of course, you can ask them via chat here also, but perhaps it's more efficient to do this with a Zoom conference. Yeah, so far to the exercise groups. Then another point is, of course, always grading. I put question marks here because it depends a little bit on how things proceed, but the likely scenario will be that there will be a final, that there will be just a final. Usually I do it differently, but at the moment I don't see another solution. And I announce it right away. When I compose a final, then I typically use at least 50% of the homework problems. Yeah, so anybody who has solved the homework problems has a 100% chance to be successful in the final. Yeah? And the other problems, 25% of the other problems will be similar to homework problems, but not identical. And the other 25% we invent newly, or we use homework problems from past years or something like that. Yeah, I think this is a fair setting, and hope that it will be successful. Yeah, and this makes it clear that you really should solve the homework problems. Yeah? If you don't, then your chances in the final, I would say, are not so great. Books. Which books do I use? Yeah, so most of the stuff that I discuss here is actually from Boyd's book on nonlinear optics. Yeah? And actually, this course is just a few chapters from that book. Yeah? The other material I took from this from the book by Zernike and Mitwinder, yeah, a cheap book, yeah, Applied Nonlinear Optics, Dover Publications. Yeah, so the name Dover Publications says it already, that it is an economic book, but it doesn't cover the entire material that I discuss here. There's another book here by Sauter, Nonlinear Optics. I took a little bit from that book, but I'm not sure whether it makes sense for you to buy this book. Yeah, so if Sauter is listening to this lecture, then he's probably angry, but I can't help, of course. Okay, so do you have questions? Questions? No questions? So otherwise, I would start with the first chapter. So repeat some things, some concepts from linear optics. Yeah? So-called linear optics as opposed to nonlinear optics. So the classic curriculum of nonlinear optics deals with the nonlinearities of the refractive index. Yeah? So the refractive index is known to most of you as a constant, as a material constant. But it is constant, that it's constant is only an approximation. Yeah? And well, in order to dig a little bit deeper, we have to look at the susceptibility. By the way, these are pages from my script, and the script is, I put it on Moodle just a few hours ago. You may not have seen it so far, yeah, so you can just download it. So, why do we need this? Well, if you look at the Maxwell's equations, you see that they contain the electric field, but also the displacement field. I call it usually the D field. And both are linked by the material or the constituent equations that you see here, right? And the refractive index is just the square root of the dielectric constant of the material. Yeah? And nonlinear optics starts when n, when the refractive index becomes dependent on the field strength. Yeah? And when I say on the field strength, then we regularly mean the electric field strength. Yeah, so there's hardly any nonlinear optics dealing with the magnetic field strength unless you go to relativistic intensities. At relativistic intensities, the magnetic field and the electric field are of comparable strength, and then of course also the magnetic field may play a major role. Yeah, so we are not going that crazy in the field strength. We are mostly concerned with optics where the material still has a chance to survive. Yeah? So we want to build a laser or so with nonlinear optics, and we don't want to blow it up. Yeah? So this limits the intensity that we are talking about to the range of 10 to the 10 watts per square centimeter, 10 to the 11 perhaps. 10 to the 12 is already quite critical, and 10 to the 13 is certainly beyond. Good and bad. In order to make a connection between the refractive index and the susceptibility that I briefly discussed already, we write the D field in the following form. Yeah? So we write the D field as the sum of the electric field times the field constant plus the polarization. Right? And for the polarization, we make this expansion here that's typical of linear optics. Yeah? So the mouse doesn't work. So first technical issue here. So maybe I try this here. No. It did work. Here it works. Do we see this now also on the? No, we don't see it here. Here it came. Okay, well, I tried this way. So you see that we make this linear expansion of the polarization, and we just substitute it here, right? And then we factor the E field out, and from this you immediately see, if you compare it to the form here, you immediately see that 1 plus the susceptibility is equal to the refractive index squared. Huh? Well, now the refractive index appears here as a scalar. Yeah? However, if you have an anisotropic material, and in nonlinear optics these are particularly important, then a scalar is usually not sufficient to describe the material. Yeah? And therefore, we will also have to discuss about anisotropic media here in particular. So now let's try to make a model, to make a more or less microscopic model of the susceptibility. It's called the Lorentz Model. And you see how modern this field is, because it's the same Lorentz who drew up the Lorentz contraction, yeah? So who made very important contributions to the theory of relativity. So the Lorentz model. So what's the idea? Yeah? So the idea is to get well, what we want to try is, as I said, a microscopic model of the refractive index. And now, if you think about the refractive index in the way you normally think about it, so I've drawn here a kind of a reference wave right? And now I put in the same wave, I put a piece of glass that has a certain refractive index. Now we know, of course, that the wavelength is shorter in a piece of glass with a refractive index that's higher than 1, that's larger than 1. And therefore, you see that what lined up here, so the minimas here lined up here perfectly, they don't do this afterwards. So there's a phase shift between both. Yeah? So this is, so this is very familiar to everybody who attended an elementary course on optics. So now a different way to understand it. So the idea is that that this field here goes through this material, and what it does there, it's an electric field, it produces polarization, right? So you can imagine that a part of the electric field is absorbed in order to set up this polarization. It's a time-dependent polarization, an oscillating polarization, right? So some part is absorbed and sets up this polarization. The other part goes through. Well, and then we have an oscillating polarization. Oscillating polarization means that we have oscillating charges, and oscillating charges are accelerated charges. They produce electromagnetic waves, right? And if you do it right, then you will find that these oscillating charges, they emit another wave, but this wave is phase shifted to the with respect to the original wave. Why? Because we will treat the molecules inside here, we will treat them as harmonic oscillators, and now it depends on how close you are to a resonance. And you know that in a driven oscillator, there's always a phase shift between the driving frequency and the displacement of the oscillator, right? So what we have here now are two fields, two oscillations that are phase shift with respect to each other. We add them together, so what you see here, and out comes another field, well, which is just the same than this field here, right? If you add two signs with different phases, you get a third sign with still a different phase, right? And you just need to do a little bit of trigonometry in order to find out how this works exactly. So this is the idea. Yeah? This is the idea that's written up here, right? And now, once we know what's going on, we do the math. Yeah? So what we do here is that we write the differential equation of a harmonic oscillator, of a driven harmonic oscillator with some damping that you see here. Right? So this is the damping coefficient, here the resonance frequency, and here is the driving field. Yeah? So in this driving field here is written in this form, and it's a little bit hard to see here. Yeah? So maybe a better projector would be nice here. What you see here is that I put a tilde on this E field. And whenever I put this tilde on the E field, then I mean, now it's a little bit bigger. What did you do?
I switched off your video, but then people in the chat can't see you. So
Okay, this is then looks a little bit, then my voice is from the off, but that's okay. So you see a tilde. Oh, I can't do this because they wouldn't see me. I put a tilde here on this E field, and whenever I put a tilde, then I mean that that we have the full time dependence of the field, right? So it's something that oscillates quickly, loosely speaking. In contrast, we will also use the amplitude, right? That you see here. Here, when I write it without the tilde, then I mean an amplitude. Yeah. And this amplitude can actually be complex, because then we can conveniently include a phase of the field, right, without much of mathematics. And there's still another notation. This is the script E, and when I write script E, then I mean explicitly a real number. Yeah? So once again, with a tilde, you have the entire field, right? And a field is, of course, a real number, right? With a trick, we can write real numbers as with complex numbers. So this we do typically here, and so on and so forth. Okay, well, we use the following complex notation. Yeah, so let me expand or explain this a little bit more. Yeah, so what you see here is that we write this field, this real field with its full time dependence, so this quickly oscillating field, we write as a sum of two complex numbers, namely the amplitude, the complex amplitude times e to the minus I omega t plus its complex conjugate. And if you do the calculation, then you'll find that this here is indeed a real number. Yeah? And as an exercise, you can just use or try this out with this other notation here, and you'll find that we reproduce here this equation 11. What we also see is that the complex conjugate of the E field is equal to the original E field with a negative frequency. Okay, but this is just for distraction, right? What we are really concerned with is actually this differential equation. Yeah, a differential equation of a driven harmonic oscillator, which describes or which approximates an electron that's bound to a molecule. Yeah? Of course, we know that it's bound by a Coulomb potential, and this Coulomb potential is not at all linear. Yeah? But if the displacement or Auslenkung, if the displacement is small, then we can approximate it in a linear way. Yeah? And this is what this equation 10 does. Yeah? So, and when we solve this, yeah, so if we use this Ansatz here and put it into this differential equation, then we find for the displacement of the electron, we find this equation here, a typical resonance phenomenon. Yeah? And when we have the displacement of the electron, then we can, of course, immediately write down the polarization, because polarization is defined as charge times, well, or the charges together times the displacement of the electron. And so we find this for the polarization, right? And this we can compare to the definition of the polarization, right? And so we can immediately identify the susceptibility with this term here, right? And actually, this quantity here is known as the plasma frequency, yeah, or circular frequency. Yeah? So what we find here is that the polarization is proportional to the electric field as expected. Yeah? And I said that this kind of is the definition of linear optics. But what we also find is that the frequency of the polarization is, of course, the same than for the driving electric field. Yeah? And everybody is very familiar with that. Yeah? So if I have a laser pointer and shine it through a piece of glass, then the red laser pointer comes out red and the green laser pointer would come out green. It would never change its color. Yeah? And the hallmark of nonlinear optics is that we produce new colors. Yeah? So in this sense, well, not only in this sense, nonlinear optics is a very colorful, a very beautiful subject. You may say he's biased, right? Well, actually, I hold the chair of nonlinear optics, so I'm entitled to be biased on this question. Well, but it's actually true. Yeah? But I have to say that the beauty of the field in the lab is in some contrast with ugly mathematics at some point. Yeah? So, and you'll see this. Yeah? So there are certain points that are not so nice. Yeah? So on paper, nonlinear optics is sometimes not so nice as in the lab. Well, I'm an experimentalist. I'm fine with that. Okay. Well, next point is that we look for polarization and the wave equation. You solved or you set up or derived the wave equation many times in your young career already, I guess, and we'll do it a few times more in this course. Here in the completely familiar way, and in a few weeks, also including nonlinear terms. So we start with Maxwell's equations, yeah? And we want to use the polarization as a source term in Maxwell's equations. Yeah? So we have Ampere's law. Well, Ampere's law actually with Maxwell's contribution here, and we have the Faraday law. Right? And what we do is that we substitute Ohm's law in Ampere's law, right? And we use the constituent equations. So D is equal to the dielectric constant, yeah, which may be a tensor actually. Yeah, so I said this already. If we have anisotropic media, then for different directions of the E field, the susceptibility might be different, and therefore also the refractive index or the dielectric number. So if we do this, yeah, and if we plug this in over there, right, so these two things here, then we get, for Ampere's law, we get this equation. Well, and then we make the first approximation. We say that the medium is non-magnetic, yeah, so that mu is equal to the magnetic field constant, and that it's non-conducting. And in optics, non-conducting is usually a very good approximation. Yeah, I like to ask this in pretty much every oral exam in electrodynamics. Yeah, if I have a uniformly charged medium, what is it? An insulator or a conductor? Right? And the answer is, of course, if it's uniformly charged, then it must be an insulator, because for a conductor all the charges are on the surface. Yeah? Okay, so we see that we have here non-conducting materials. Yeah, so this means that the Leitfähigkeit, the conductance, is equal to 0, which simplifies things a little bit. Yeah, so now we have this as Ampere's law and Faraday's law. The next step is that we apply the curl to the left and right side of Faraday's law, which you see here. Right? And then we use the famous Buck-Cup rule for the vector product. And if we apply it here to the left-hand side of Faraday's law, then we find that we get the Laplace operator, minus sign also, right? And as long as we are in linear optics, we can easily find that this here is equal to 0. In nonlinear optics, it's more difficult to argue, but we'll find, we say at least approximately it's also 0 in nonlinear optics, right? Okay, so we plug this here into here, right? And for the magnetic field, we use, of course, Ampere's law, right? And then we get this equation. Looks a little bit complicated, but if we write it in one-dimensional form, then it's immediately familiar. So what you see is, I'm afraid, a misprint, right? So there, it's of course the second derivative here. Yeah, it's not the first time that I give this lecture, but it's the first time that it catches my attention. So we have a typical wave equation, yeah? A typical wave equation. So wave equation, yeah, what's the solution of a wave equation? Of course, a wave, yeah? And here you see one example for a wave, right? So a wave is a function that you can differentiate twice and which has this argument here, right? So you see that this here is actually a harmonic function, and yeah. Well, we would substitute it here into the wave equation, and then we get what's called the dispersion relation, yeah, that k is equal to omega divided by c, and well, if you write it with refractive index, then you see it in this form. And of course, now you can use the equation that we found before and write it in this way, the refractive index. Yeah. And now let's look at this in a little bit more detail. Yeah? So the same here, just repeated. This is what we just had, and now we can just plot this thing here, and what you find is the typical, well, the typical dispersion of a medium that has just a single resonance. Yeah? So what you find is that with increasing frequency, it's hard to read here, but I say it. Yeah? So with increasing frequency, the refractive index increases. Yeah? If you're below the resonance, so if your frequency is below the resonance frequency, then you find this behavior. With increasing frequency, the refractive index increases. This is what we call normal dispersion, and on the other edge or on the other side of the resonance, we have anormal dispersion, and actually the refractive index there is often smaller than 1. If you have several resonances, well, then you superimpose them. Okay, so far to the Lorentz model. Yeah, so the next thing is that we now would look at anisotropic media. We would look a little bit at crystals. Yeah? So let's look at, and in order to analyze that, we need to look, kind of surprisingly, I would say, we need to look at the energy density in anisotropic media. Yeah? So the first thing to notice is that in anisotropic media, the electric field and the D field are, in general, not parallel. I mentioned this already. This dielectric number is not a scalar, but it's a tensor. And I explained already why. Yeah? And we would write this in this form. This is Einstein's sum convention. Yeah? So whenever you have an index that appears twice, you immediately have to think that you sum over it, yeah? That you contract it. Yeah? So by definition, this convention is this formula here. Okay, the next assumption is that the energy density and the Poynting vector that we know from isotropic media, that they are still valid in anisotropic media. Yeah? And in addition, we assume that half of the energy of the electromagnetic field is in the electric field and the other half in the magnetic field. Right? And we only look at the electric density, at the energy density of the electric field. Right? Again, from the second semester, you know that this energy density is given by 1/2 times the scalar product of E and D. And now we write it in this form. So we just use the Einstein sum convention here, right? And nothing has happened so far. Yeah? For the one reason or the other, we are now interested in the change in the flux of the energy density. Yeah? And therefore, we take the derivative. So this we do here. We take the derivative here, right? And of course, I need to use the product rule. So you see this here. I think in the script that I uploaded on Moodle, there's still a misprint, but here it's in the correct form. So I take the derivative of this here and just copy this thing here, and then I do it in the other way around, right? And what I do next is that I just rename the indices here, right? Instead of J, I write K, and instead of K, I write J, right? So in Germany, we say names are just Schall and Rauch. Namen sind nur Schall und Rauch. Names are just noise and smoke. Yeah? And therefore, I can, of course, rename them. Yeah? I could also use the index N and M if you don't like this. Yeah? So I hope this would convince you. Yeah? So now I have the energy density flux. Yeah? So we will need it in a second. But first we look at the Poynting vector. Yeah? The Poynting vector is given by E cross H, right? And it's the power flux per unit area. Yeah? Now we use the Gauss-Ostrogradsky theorem. Yeah? So usually we just say Gauss theorem. Ostrogradsky, a Russian mathematician, founded it about the same time than Gauss and gave a proof of it in particular. And yeah, and with this we can find the power flux into a unit volume as the divergence of S, yeah? Of the Poynting vector, right? And then we take the electric part of it, and we say that this must be the same thing that we just calculated. Okay, so we have to use now, we have to do the divergence of the Poynting vector. And here I do it, I use another vector identity. Right, so divergence of A cross B is given by this expression here. And if I apply it to to S, well, then I find this equation here. Right? And we take only this one here, this part here, and compare it to what we had here. Right? And it should be equal. Yeah? So I do exactly this. Yeah? So I write this term here on the left-hand side, and I write this term here on the right-hand side. Yeah? Nothing has happened. Indices perhaps renamed. But what you find is that this is only possible if epsilon kj is equal to epsilon kj, jk to kj, right? In other words, this tensor here must be a symmetric tensor, right? And this is very nice, yeah? Because if you look again at this energy density, right, and you write it out, then you find this lengthy expression here. right? And using now the symmetry, you get 3 terms less, yeah? So therefore this factor of 2. Well, yeah?
Is there also a physical interpretation to the symmetry of the tangent?
Sorry?
Is there also a physical interpretation of the symmetry?
Yes, this will come later. Yeah? So we'll yeah. So the question was whether there's whether there's a physical or perhaps even an intuitive interpretation of what we just did. And the answer is yes. Yeah, so we'll come to the index ellipsoid in, well, probably not this lecture, but in the next lecture. So what I do first is, now that I change to a coordinate system, the thing that I have to say first is that this is, of course, the equation of an ellipsoid, right? And it lies somewhere with some orientation in space. Yeah? What I do next is that I change my coordinate system such that the coordinate system is aligned to the semi-axis of the ellipsoid. Right? And if I do this, then all these ugly terms here are 0, right? Just by changing the coordinate system. Right? And we call this the principal axis system, or in German the Hauptachsensystem. And because it's a German lecture, I use HAS as an abbreviation, yeah, just to be a little bit patriotic. You can also call it PAS, yeah, and cross it out in my script. I have no problem with that. Okay, so and in this principal axis system, so we can write it nicely in matrix form. Yeah, so for the first time, this is the same as this here, right? We write it nicely in matrix form. It's a diagonal matrix, right? But each of these items is in general different. Yeah? If all of them are equal, then we call it an isotropic material. If 2 of them are equal, then we'll find that it's a uniaxial crystal. Yeah? And in the other case, it's a biaxial crystal. And where this comes from, we'll learn next time. Because before we do so, we need to derive another equation, namely the Fresnel equation. Yeah, so Fresnel was the famous French physicist who proved that light is a wave. Right? So it's not so appreciated any longer that it was actually Fresnel who proved that light is a wave. Yeah, so most people would say it was Thomas Young, and in some sense they are right. Right? But the real proof indeed came from Fresnel, and he also discovered, together with Arago, François Arago, who was a really remarkable person. Yeah? He was not only a physicist but also a politician, and a particularly honest person, I would say. Yeah? So so if you look for a role model, then he might be a good starting point. François Arago. Yeah? Good. So wave propagation in an anisotropic crystal. Yeah? We're still dealing with linear optics, but wave propagation in a crystal can already be quite a complex thing, but we try to keep things simple. So the first thing is, we restrict, of course, again to monochromatic wave. And we have the wave vector now. We use here a unit vector S in order to give its direction. Right? So this is a unit vector normal to the wavefront, perpendicular on the wavefront. right? So now a little exercise, most of you probably know it. So if I have a monochromatic wave, a harmonic wave, just a harmonic wave, then instead of these cumbersome differential operators, I can just replace the Nabla operator with I times k. So I times the imaginary unit times the wave vector, right? And if I use this abbreviation here, then I would write it in this way. And the temporal derivative I can just replace with the imaginary unit times omega. Yeah? Try it out. You'll find that this holds. And accordingly, for a monochromatic wave, I can write Ampere's law like this. Right? So I just replaced the Nabla operator, nothing else. And on the other side, I replaced, of course, the time derivative with I times omega. And I do the same thing for Faraday's law. Right? Yeah, really useful, these things. Trivial, but useful. Well, and if you look at this, you find you can establish several things. Of course, if you look at this equation, then you find that the D field is perpendicular to S, and the D field is also perpendicular to H, right? Because we know that, well, everybody knows the properties of the cross product. And we can look at in the same way to Faraday's law. H is perpendicular to S, and H is also perpendicular to E, right? Well, this has two consequences. Actually, it has three consequences. Well, the first here is trivial, and everybody knows it. An electromagnetic wave is a transversal wave. Yeah? So the E field and the H field, they oscillate perpendicular to the wave vector. Yeah? And what you also find is that if you look at this here, yeah, so you find that D, E, and S are perpendicular on H. Yeah, so I show this here. So the H vector, the magnetic field, or H field rather, comes out of the plane of drawing, so points towards U. And then we find that the E, D, and S, that they are all perpendicular to H, which means immediately that they are all in the same plane, right? Well, there's a third thing that's remarkable. You find here, or you see here, the Poynting vector in pale green here, right? Which is E cross H. E is perpendicular on E and perpendicular on H, so it goes in this direction. Very strange. The Poynting vector describes the direction in which the energy goes, the energy flux goes. And it goes in a different direction than the wave. Yeah? Disturbing, but true. And it has consequences, of course. For example, if you try to do nonlinear optics with crystals, it may create a problem. So, the next thing is, so we want to derive the Fresnel equations, I said. Yeah? Fresnel equations, they are there in order to derive the refractive index in a crystal. Yeah? Okay, so what we do, yeah, so we look at these two equations here, which are kind of Ampere's and Faraday's law, right? And we'll eliminate H, because in optics we are mostly concerned with the electric field. We eliminate H by substituting the one into the other. Yeah? So I do this here. Right? Looks ugly, but it looked ugly before. Right? In the same way as we did when we derived the wave equation, we use the Buck-Cup rule here. But things here are a little bit simpler here because S times S. Yeah, so unit vector times unit vector, this is of course equal to 1. Right? So we are left only Yeah, so if you solve for d, then you end up at this equation here, right? Okay, well, this doesn't look nice, and therefore we look at this equation component by component. And actually, I do it just for the x component, and for the y and z component, it works in the same way. Yeah. So we just look at the x component. So we write this here for the x component, and you see nothing has happened, just the x component. I introduced some abbreviation here, n bar squared, yeah? Just to make it a little bit less involved here. Okay, so I do this, bring this here to the other side. Yeah, so you see this here, and I have on the right-hand side, I still have this term here. And now I solve for dx. Yeah, so I factor it out here and divide through 1 minus n squared over epsilon x. Yeah, so this is this equation now. Right, and well, we can divide here through this n bar squared. Then it looks like this. Right, and yeah, in order to get rid of this minus sign, I just flip these two terms here. Okay, now we know, now we start with another ingredient. We know that s times d, yeah, so this unit vector here, s times d, that this is equal to 0. Scalar product, yeah, and this immediately means that sx times dx plus sy times dy plus sz times dz, that this is equal to 0, right? And now we use these expressions here and plug it in here, right? Nothing else has happened. That's it, right? And we get this interesting equation, right? Next, I remove these abbreviations that I introduced here at this point. Yeah? And we have this equation here, and this is Fresnel's equation in the principal axis system. Yeah? Doesn't look nice. Yeah? Well, we didn't even start with nonlinear optics. And the question is, of course, for what is it good? Yeah? No? Well, suppose we have a crystal lying somehow in space, and we shine with a beam of light on it. Yeah? Then it's certainly an interesting question, what is the refractive index? Yeah? So you have just a crystal, shine with a piece of light on it, right? And now the question is, you know the tensor of this thing here. You know the epsilon x, epsilon y, and epsilon z, right? But you don't know the refractive index for this beam of light. Yeah? And it's Fresnel's equation that gives the answer. Yeah? Okay. Yeah? So in fact, Fresnel's equation not just gives one answer, Fresnel's equation in general gives two answers. Yeah? Because this equation, so Fresnel's equation, is quadratic in n squared. Well, strictly speaking, it gives 4 solutions, but the negative sign has no physical meaning. Yeah, so we have 2 solutions, n prime and n double prime. And this means immediately, if you look at this equation, for example, right? So if you have two solutions, then there are also 2 d fields, and of course also 2 electric fields. Yeah? Ah. Is it new for you? Is this new for you? No? Why not? I didn't understand. Yeah, okay, but how is the effect called that you associate with this? Exactly, birefringence. Yeah, this is what we get. Yeah, so this is what comes out of the Fresnel equations. Yeah, so the Fresnel equations, they tell you which refractive index each of the polarization has or sees. Yeah. Okay, let's go on. Yeah. So we have two refractive indices, right? So there exist 2D fields. We call them in the same way, D prime and D double prime. And now you can make an exercise and find out that both are perpendicular to each other, right? So now some final remarks for today, and I'll stop after that. For a given direction of the wave vector, an anisotropic crystal can only transmit two waves. So there are only solutions for these two waves that are linearly polarized, here's a D missing, in one of two mutually orthogonal directions. Yeah? And these two waves see two different refractive indices. Yeah? Now you could ask, oh, he says only two waves are allowed. What if I take a different polarization? Well, the answer is simple. Then just decompose this different polarization in the two allowed ones, and you are done. Yeah, so actually, this is not really a restriction that only two waves can be transmitted. Yeah? Okay, so I would stop at this point here this time. So a quarter of an hour short of the actual time, and continue next time with the index ellipsoid in order to answer your question, right? And we are still preparing a few figures that illustrate it nicer as I could do it today. And with this, I thank you for your attention, and we look forward to see you next Monday. Good.
Can I ask one question?
Sure.
If you have different refractive indices for left and right and polarized light, what? Oh, yeah, right. So if we have a different refractive index for left and right-handed polarized light, like what assumption did we not make to make that happen?
What was that last?
So you can have different, like birefringence, but then not for linear polarized light, but for left and right-handed polarized light.
Yep.
Did we make an assumption in the tensor that, like, if you want to create that effect, like?
You can, of course, always look at. So what you describe is circular dichroism. Very important effect in well, some fields of nature actually, and also some fields of physics. You can always decompose. You can always decompose circular polarization with two phase-shifted linear polarizations. Yeah? In this way, you can of course always treat it. Yeah? On the other hand, you can also use as a basis circular polarization. Right. But of course, if we talk about birefringent crystals, then of course the phase shift, the phase shift that might occur there is very important. And after all, birefringent crystals can be used in order to produce circularly polarized light from linearly polarized light. Yeah, so what you use is just the different optical path lengths for the two different polarizations. Yeah, so again, you would Yeah, actually, it's a nice example for what I just said, right? So I said that there are two allowed directions, right? And what you do in order to produce circularly polarized light is that you put your crystal at 45 degrees, such that your incident polarization must be decomposed in the two polarizations, one parallel to the crystal axis and the other perpendicular to it. They see two different refractive indices, and therefore, well, the nature of that light changes. Right. Good. Thank you.